We're going to do a buffer demonstration now. So how does a buffer work? A buffer is a solution which has components that are able to act as an acid and a base. Bicarbonate is the primary buffer in our blood that protects our blood from changes in pH due to extra acids or bases we add to our system. The bicarbonate ion is able to accept a proton, aka be a base, through this reaction. Bicarbonate ion is able to donate a proton, aka be an acid, through this reaction. So how will we demonstrate this? We have a buffer, bicarbonate buffer in this beaker and deionized water in the other beaker. And the first thing we want to do is test the pH of each before we add anything to them. So this is a pH strip before it's dipped in any solutions. And then once we've dipped in the solution, we can line it up and match the colors on the strip to the box to find out what the pH is. So in the case of the bicarbonate buffer, we see that the pH matches nicely with a pH of 8. So that's our baseline pH for the buffer solution. And over here on the right, we see that the deionized water has a pH of just about 7, which is exactly what we'd expect for water. So the next thing we're going to do is we're going to add some hydrochloric acid and sodium hydroxide, hydrochloric acid being our acid, sodium hydroxide being our base, to each of the solutions and then test what happens to the pH. So first we add about 40 drops of the hydrochloric acid to the deionized water. We retest the pH and we see that the pH has dropped dramatically from an original pH of 7 to now pH 0. So we went from neutral pH 7 to extremely acidic, which is exactly what we'd expect for deionized water with acid added to it. We do the same for our buffer solution. We add about 40 drops of the hydrochloric acid to our buffer, retest the pH, and we see that the pH is still just about pH 8. So almost exactly the same as what we had before, and this is because the bicarbonate ions have absorbed the acid to form So the next thing we want to do is see how the base affects our water. So we add about 60 drops of the sodium hydroxide base to the deionized water, retest the pH, and we see that the pH has increased from pH 0 when we added the acid to now a pH of 12, which is basic. Again, it's a dramatic increase in pH, so the water has gone from acidic to basic, just as we expected. We do the same for our buffer, add about 60 drops of the sodium hydroxide base to our buffer. We retest, and we see the pH of the buffer still remains pH 8, the same as we had before. So the OH has stolen a proton from the carbonic acid here. This reforms our bicarbonate ion, right? So by adding the sodium hydroxide, we've essentially reset the buffer to a certain extent. Okay, now we're going to do a little visual testing. So we have the pH tests that we did, but now we're going to use some indicators. The first indicator that we're going to use is called phenolphthalein. Phenolphthalein changes colors from clear to pink at about pH 8. Above this pH, it gets darker incrementally, right? So if you had something that was pH 10, 12, 14, that would be a darker shade of pink. So let's check out what happens. So adding drops of acid to what we know is an alkaline solution. We see the pink color fading away. indicating that we've made the solution acidic. Now we're adding about the same amount of acid to our buffer. You can see there's some bubbles forming there on the top. That's carbon dioxide bubbles forming. When we mix the buffer, you see more of those carbon dioxide bubbles. You see the pink color lighten a little bit, right? But definitely not as dramatic as the deionized water. Okay, so next we're going to use the indicator bromothymol blue. So we have bromothymol blue is a blue color and when you're above pH 6. When you go below pH 6 and get into acidic territory, you go from blue to yellow. So we're going to add the bromothymol blue. It gives us an idea of what our starting pH is for both the buffer and the deionized water. And then we're going to add some sodium hydroxide and see what happens. So we see the deionized water started out yellow, indicating that it was an acid. And if we add a few more drops of the sodium hydroxide, we get that really dark pink, but we also get the bromothymol blue turning blue, so the blue and the pink combined make this pretty purple color. So we see the buffer starts out blue, indicating that it's above pH 6, so not acidic. And even after adding the same amount of sodium hydroxide, we still get the buffer being sort of blue. We add even a little bit more and we get a slightly purplish color, right? So indicating that we've moved the pH very slightly. So this demonstrates that a buffer is capable of playing an important role in maintaining the pH of solutions. This is obviously vital for living systems. Bicarbonate buffers can absorb both acid and base according to those reactions below. Buffer capacity, the ability to maintain pH, can be exhausted if too much acid or base are added to the solution. So in those later videos that we were just looking at, you can see that the buffer starts to lose its ability to resist change to the pH, right? So buffer capacity is based on how much of the buffer components are available, so the concentration of the buffer, and also how much of the acid and base are added to the solution, right?